Okay, so we have this definition so far for work, but you need to remember this is for a constant force. Okay? So it can be in a different direction. It can be at an angle to its displacement, but it has to be constant. What if it's not constant throughout the displacement? Okay, so we need to address if F is not constant throughout the displacement. So for example, if I move it through like this, right, in a whole path. So this is my path, and so this is the initial, this is the final point, and I'm applying a force this way. And now you see, if I at every point of the object when it moves over here, how are we going to deal with if the path is curved? Okay. So in some sense, you see the angle, this is trying to move this way, but the force is applied over here in this way. So it's changing all the time. So how are we going to do it? Let me try to clean this up a little bit. Just the path. We use the idea of calculus. We split this into little segments first. Okay. And think about it this way. So instead of looking at a big displacement from initial to final, we look at a small displacement over here and call that dr. Okay, that is what dr is. It's really just giving a symbol for the idea of splitting into small segments like this. Now, this is if I apply a force like this over a short enough displacement, this is going to be a straight line, and this is going to be a constant force, because from here to here, let's say t equals to 0, and this is t1. If I chop this into little segments of time, this time is so short that the force is not going to change. Okay, so in this part, the work done from t equals 0 to t equals to 1, so from 0 to 1, let's call this point 0, 1, 2, 3, 4, dot, 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 right, like this, all the way to f. From 0 to 1, the work done is f times f dot dr, because f is going to stay constant throughout this short amount of time. It might change later on, but I'm going to look at it segment by segment. Okay, and work done from point 1 to point 2 over here. So as you can see, my force might completely change. But yeah, if this is a short enough segment, the force is not going to change between here. Okay, so it's going to be the force at point 2. So let's put that as at point force 1. So at point I'll just put as force 1 during this period, and force 2 because I don't want to duplicate. I don't want the same variable over here. dr1 like this, and dot dr2. Okay, so you can now add everything together. So the total work done is you add up all the work, right, from the period. So that is like sum of fi dot di, right, where I goes from 0 to however many steps you have. Now, to actually get the whole curve, you want to shrink this as small as possible, so that you really approximate fully the curve. How small should I shrink dr? How many pieces should I chop? The more the better. If I chop it to infinite pieces, so if I take the limit of n go to infinity of I from 1 to n, this, okay, so I'm basically doing this and take the limit. Now we have a special name for this symbol. It's just an integral. Okay, and I'm not going to prove to you how taking the limit actually goes match with that power rule you've learned, that it goes to n plus 1 and divide by n plus 1 like that. So that's a math problem. Since this is a physics class, I'm not going to explain to you there, but just the concept is part of the course to understand. Basically, integral is adding infinite pieces. Okay, so when you chop into infinite pieces, it also makes the each displacement infinitesimal, makes infinitesimal displacement, and the force during that little period will be constant. So you can use this at every infinitesimal piece. So you can use f dot dr vector at each infinitesimal piece, and you sum it together. So this is the full definition of work. Okay, so you can put that in the box. If someone asks you for a definition, you can put it this way. So here you say this is the force at each point along the path. This is the initial, so I is the initial point of the path. F is the final point of the path. And dr is an infinitesimal displacement along the path. Okay, so this is the dot product, right? So infinitesimal displacement along the path, the force at each point along the path, the initial point along the path, the final point along the path, and you've defined all the variables that appear over there. Okay, so so how does it connect to the definitions we have learned so far? We'll quickly see that. Well, if f is a constant, so this is the general definition. But if f is a constant, you can pull that out. So you have this dot dr like this. How do you do this integral? So that's a dot product. How do you do this integral? Well, at first you might be very intimidated by that, but you can remember what is integrate dx. Well, what's integrate dx? Well, that's 1 dx essentially. I'm integrating 1 dx. I'm just not writing the 1, right? So that's 1 is basically x to the power of 0, right? So if you integrate that, you will increase that by the powered by value of 1, and you'll divide by the new index, right? 1. So it's just x, right? So when you integrate 1, you get x, right? So if you essentially integrate dx, you get x like this. How about if I have a limit? What do you do? Well, if you remember the rules of integration, you do the integration and then you need to write this symbol, and you plug in the top, subtract by when you plug in the bottom. And if you see, this is final minus initial, this is just delta x. Okay, so you understand if I put without limit, this is just x. With the limit of initial and final, it gives me delta x. So this is the same thing if I put dr vector. Well, it's going to be integrate dr is going to be r. Okay, so it's just replace this with x, right? This is r, but you need to put initial and final. So it's r final minus r initial, right? So the final position vector minus the initial position vector, that's the displacement vector. Right? That's the change in position. Remember, displacement is change in position, right? Over here, with this whole thing is basically f dot change in position from initial to final if you want. Okay, so we got from the general definition, if f is constant, it reduces to this, the initial to final, so we don't even need to write this if you understand that's the displacement. And obviously, if they are parallel, so it reduces further because this is identical to f dr cosine theta. This is a mathematical identity. Dot products is equals to that. And if they are parallel, it's just f times dr. And you can choose the x-axis as the, you can choose whatever axis they are, because if they're parallel, they're basically, it's a one-dimensional problem. So usually people just use delta x like this. Okay, so the three cases are each, we'll look at some examples. If this is abstract to you, don't worry too much. really just know when to use which definition. I've written that many times, but you can in your notes put in the cases, right? This is when f is constant, but not parallel to each other. This is when f is constant and parallel to each other. This is in general when f is not constant and not parallel to each other.